pressing? I honestly can't. Okay. And get started. I'm recording. Okay. So another thing for this exam, when you get there, you will get the ACS part first. So the ACS official exam, multiple choice. Total test time is 2 hours. So you'll just take the ACS exam at your own pace. Whenever you're done with it, you'll get a TA. They'll come over and give you Beans exam, and then we'll work on that. So I would say try to allocate roughly an hour for each. But again, you don't have to like wait until that hour to get Beans part. You can just get the Beans part whenever you're done with the ACS portion. And there's not going to be a facts section for Beans portion because that's pretty much what the ACS exam is. So yeah. So we'll just go ahead and get started with nomenclature. There's not too much new, luckily, other than amines. But luckily that's not too bad. Okay, I feel like I'm a little bit loud. Okay, so getting started with the first question. Amines are going to be pretty low in the priority list, so even though we've learned them last, they're very low in the priority list. You can see they're all the way down here, even below alcohols. So our parent for this one is actually going to be the ester that's kind of in the middle there. And so for esters, the carbonyl part is going to be kind of like the main part. So we're just going to start numbering from there. So 1, 2, 3, 4, 5. That gets us to a substituent, so that'll be just the whole chain. So that's going to be a pentane, and then the ending for esters is 08. So that'll be kind of like our main part. And then for the ether part, or the ester oxygen, I guess, again, we just number down the chain. So we got 1, 2. That gets us to a substituent. So this is going to be ethyl. And then as for the substituents, this benzene ring is going to be a phenyl. Remember, phenyl is when it's just the benzene ring by itself. And the benzyl is when it has an additional CH2 group. So this will be 2-phenyl ethyl. And then over here, attached to the main part, we have this amine group. And both of the parts coming off of the amine are going to be ethyls. So this is going to be diethyl. And then whenever the amine is a substituent, it's called amino. So you just say diethyl amino. And that's coming off of carbon 5. So then we're just going to put it all together. There's no RNS or ENZ or any stereochemistry. The ether oxygen, ester oxygen part is going to go first. So we've got 2-phenyl ethyl. And then space 5-diethyl amino pentanoate. Okay, any questions on that first one? All right, we're going to go ahead and move on. Okay, so for this one, we only have this amine here and we have an alkene. So alkenes aren't really, I mean, they're functional groups, but they kind of go just in the name of the molecule, kind of, I don't know how to say it, but the functional group for this one is going to be the amine. And so since this is going to be the parent, we're going to start numbering from there. So we've got 1, 2, 3, 4, and then we could either get 5 or we could get 6 total. So we're going to go with the one that gives us the longer chain. And then that alkene starts at 5. So we'll just have 5-ene as a reminder for that. So our longest chain is going to be 6 carbons. So that's going to be a hexane chain. And then again, we've got that alkene. We're going to do hex 5-ene, or you could do 5-hexene. And then for amines, the parent name is just amine, and it just goes right at the very end of the name. So this is going to be hexene amine. But similar to alcohols, we do have to note where the amine is. So since this one is coming off just of the first carbon, this is going to be hexene 1-amine. So that's going to be our parent name. We have to do our substituents. So whenever we have substituents for an amine, they'll just be kind of substituents like to the whole chain. The only difference is that you'll denote them as N. So we have 1, 2, 3, 1, 2, 3. So these are both going to be propyl groups. So this is going to be dipropyl. And they're both coming off of the nitrogen. So this is going to be N, N, dipropyl. And whenever they're the same like that, you just throw them on the same N/N, or the N, N. So those are the substituents for the nitrogen. And then we also have this little methyl group over here at carbon 4. And that's all the substituents. We don't have to do any stereochemistry in this case because the double bond has got 2 of the same group on the left over there. It's just hydrogens, so we don't need to do stereochemistry for that. And then we just have to put it all together. So we've got M and P. So M is going to come first. So we've got 4-methyl N dipropyl. And then our parents was the hex 5-ene 1-amine. Okay. Any questions about that one? Like if you started from the left instead? Yeah. So that would just be like dipropyl 5-hexene. Are you saying like 1-amine? Yeah. Oh yeah, so for this one, it's similar to alcohols. So the amine could be anywhere on the chain, so you have to denote the specific carbon that it's at. So that's why you put number 1. Yeah. The only exception would be if there's like a common name to something. So that's why like, for phenol, we don't have to say phen-1-ol, because phenol is kind of including that as part of it. But yes, in this case, it's kind of just like a normal alcohol linear chain, so you would put the number. Yeah, that's a good question. But then yeah, you could also do 5-hexene if you want to put the 5 before too. I just put it in the middle because that's what I did. Okay, any other questions on that one? Okay, we'll go on to number 3. Okay, so we've got an ether, and we've got an aldehyde, and we've got a ketone. So ketone, ether, aldehyde. Remember, aldehydes are going to be higher than ketones, so that's going to be our parent. So we're going to start there. 1, 2, 3, 4, 5, 6, 7. So this is going to be a heptane. And then the ending for aldehyde is going to be hept and al. So just al at the end. And so for this one, since aldehydes are always on the end of the chain, then you wouldn't have to put the number. Otherwise, we've got a few substituents. So remember that ethers are going to be named as alkoxy. So this is going to be 4 dash, there's 2 carbons, so it's going to be ethoxy. And then 6 is a ketone, and that's going to be the oxo group. So those are our substituents. And then we do have some wedges and dashes, so we're going to have to do some R and S here. So we're going to start from this carbon. Hydrogen's always going to be 4. If we go to the next atom, we have a carbon, and we have an oxygen. So the oxygen is going to win. And then between this carbon and this carbon, they're both CH2s. So we're going to go to the next one. So on the left, we have a ketone. On the right, we have another CH2 group. So the left side is going to win. So just move this down here so you can see it a little bit better. So this is going to give us S. And since we only have one S, we can just leave the number off. Or if you'd like, you can just put where it's at, which would be at carbon 4. we've got 4S, and then E comes before O. So we've got 4-ethoxy, 6-oxo, and then heptanal. All right, any questions on that one? Cool. All right. Any questions on any of the other nomenclature before we move on? Okay. Yeah, like I said, luckily nomenclature isn't too much different. And then again, we are skipping the facts because that's just going to be the ACS part. So we're just going to get straight into reactions. So you're going to see kind of a mix. There's going to be some Orgo 1 stuff. There's going to be some stuff from earlier this semester. And then there's going to be all the new reactions that you've learned. So to get started, we have MCPVA. This is going to be our epoxide forming reaction. So step 1, got our epoxide. And then CH3OH and H+. So this is going to be our acid catalyzed ring opening, or epoxide opening. And so for this, you'll want to remember the BLAM acronym. So base, least, acid, more. So that just tells you where the nucleophile is going to attack. So in this case, since we have acidic conditions with H+, our CH3OH is going to attach itself to the more substituted position, and that's going to kick the epoxide to the other side. So it's going to attack at the more substituted. That's going to kick the epoxide out. And then the H+ will protonate the epoxide oxygen. So that's going to be our end product of step 2. Step 3, we've got one of our chromic acid reagents. So this is going to be a strong oxidizer. So this is going to take the alcohol to a ketone or carboxylic acid. It does not affect ethers, so the ether is just going to be chilling. And so since we have a secondary alcohol, it's just going to form a ketone. And then step 4 is the Wittig reaction. I believe this is at the end of the ketones and aldehydes chapter. So chapter 18, I think. Don't quote me on that. But this one, you're essentially going to attach the alkyl side where the ketone is. So I like to literally just think of like I'm taking the oxygen off and replacing it with the carbon and whatever is attached to it. So this one, it's a carbon with 2 methyl groups on it. So that's exactly what we're going to attach to the ketone position. Got our double bond, we've got our carbon now, and then it had 2 methyl groups on it. So that's going to be the end product of that step. Watch out because sometimes for the Wittig reaction, it will form the trans isomer if the groups are bulky. In this case, we have 2 CH3 groups, so there's not really a difference. But sometimes she'll throw like a benzene or something, and you'll have to watch out for that. Any questions on this first reaction? Yeah, like the Wolff-Kishner. Mm-hmm. Yeah, I see what you're saying. Mm-hmm. Another one is like NaOCl, maybe? Yeah, I think that one might work too. I know that there's a Cl in there, but I think since it's attached to the oxygen, it should be fine, question mark. But I think that one also is selectively for secondary alcohols too, but. Mm-hmm. Okay, we're gonna move on to the second set. Okay, so if you forgot Diels-Alder, review it because it will be on the exam. So here we have a diene, and then we have a dienophile over in our first reaction. And so remember, dienes are going to have the donating groups. This one just doesn't have anything, which is fine. And then the dienophile is going to have an electron withdrawing group on there. So your carbonyls, nitriles, stuff like that. And so what I like to do is I like to kind of orient it so it looks a little bit better. Here it's a little bit hard to see how it might react. So I just like to line them up like they might react in real life. So we got first step. So double bonds are going to come out and attach to themselves, form the cyclostructure. So this one's going to form a cyclohexane. And then don't forget that this bond right here will form the new double bond. And then we had our aldehyde coming off of this carbon. Okay, and so we don't have to worry about like the 1,3 or 1,2 addition or anything like that because there's no donating groups, so this one can add wherever it wants. So that's going to be step 1. Step 2, we've got Ag2O H2O THF. So this one it's not Tollen's reagent, but it's similar to the Tollen's reagent, where it turns a aldehyde to carboxylic acid. And this one's very mild, so it doesn't affect any other groups in there. So we're just going to turn this one into a carboxylic acid. Right. And step 3. So step 3 looks a little bit weird, but this one is going to be the direct amide synthesis. So usually for amide synthesis, we use like a acyl chloride because they're more reactive. But under these conditions, we can form the amide with a carboxylic acid. And so we just have a ammonia. So we're just going to add a NH2 group and form our amide. And then this one is also pretty special. This one's chapter 19, I believe. And this one's going to be the Hoffman, it's either the elimination or the rearrangement. I can't remember. Rearrangement? Okay, cool. That's what I thought. So this is chapter 19 again. And so this is going to just get rid of this carbonyl and its carbon. So we're kind of shortening the chain by 1 carbon essentially. So that is going to take out the carbonyl, and we're just going to be left with that amine coming straight off of the ring. So that's a pretty interesting reaction. Any questions on this set? Mm-hmm. Yeah, no. In this case, since there's no donating groups, you can put it anywhere. When there's donating groups, that's when you're going to do the 1, 2, 1, 4 addition thing. All right, we're going to move on to the next set. Okay, so we've got LiAlH4, our favorite reducing agent. So this one is just going to take the amide and it's going to turn it into an amine. It's just going to reduce the carbonyl. 1, 2, 3. Okay, and then step 2. This one is also pretty unique. So what this one does is it forms a double bond in kind of a strange way. So here, let me draw it off to the side for you guys. So each of these CH3Is are going to kind of surround the nitrogen. And so eventually we're going to get something that looks like this. And so this turns the nitrogen into a good leaving group. And so then from there, with the rest of the reaction, we form a, what's it called? Alkene. So in this case, since we have 5 carbons, 1, 2, 3, 4, 5, we're going to form a 5-carbon alkene. Okay. All right, so then we've got NBS and light, or sorry, not light, NBS and heat. And so this one is going to do the allylic bromination, but we do have to watch out for the heat because this one is going to be like the high temp, low temp product thing. So what I like to do is I like to draw the radical that forms first. And so that's going to form a radical at the allylic position. And then we can do our resonance with this structure to see what it's going to form. So these are our two resonance structures that we can get. And so for the high temperature, it's going to form the more stable alkene. And so if we look at this, at the difference between them, the one on the left is going to be a mono-substituted alkene, whereas the one on the right would be a di-substituted. So in this case, since we have the high temperature and we want the more stable alkene, that's what we're going to attach our bromine to. So this is going to be the product of reaction number 3. All right, and then we have NaN3. So this is kind of the end of the chapter 19 stuff that you'll learn. So this is sodium azide. You don't really need to know the name, but in case you want to. And so this is just going to attach, it's going to replace the bromine and it's going to attach I don't know what you'd call it. It's going to, yeah. So it's going to do this. It's going to have the nitrogen on the end here like that. You don't have to write it like that. You could just write it as N2 as well. So you could just show it like that. That's going to be step 4. And so this one is used to form like a few things from like nitrogen compounds. So this is, yeah, again, like the end of the 19 stuff that you'll learn if you haven't gotten there already. But then we just have another step of reducing. And so this is going to just reduce the nitrogen part to be a amine. We're just going to have our NH2. And then the alkene is not reactive enough with the LaAOH4, so that'll stay the same. The only thing will be the nitrogen that gets reduced. So that one's reaction set 3. Sure, the first step. Second step, right here. Yes. So the CH3I is basically going to attack and attach itself to nitrogen, and it's just going to surround it because we have excess. So then that creates a positive charge on the nitrogen and makes it a good leaving group. And so you don't need to know the mechanism for this one, but the Ag2O then kind of it forms, I think, an ionic interaction with the nitrogen and kind of helps remove it. And then it forms a double bond in its place, kind of. That's a good question. So it just has to do with the mechanism of the way that the sodium azide reacts. So I don't have it off the top of my head, but one of the nitrogens, the sodium azide mechanism, why does one of the nitrogens get removed? Yeah, yeah, me neither. Yeah, it's just gonna be N2. That's a good question. I haven't looked at enough tests to see. Yeah, I think it's an E2 mechanism. I want to say theoretically. I cannot say for certain, so I don't want to lead you astray. Step 4. It is N3? Okay. Okay, it's the sodium then that gets removed. Okay. Oh yeah, so I think it's like something like this instead. Okay, thank you. That is my mistake. So it is going to be N3. My bad. But yeah, I think when I was looking at the notes, it was an E2 mechanism, but I don't want to say anything definitively because I don't want to say something wrong. But yes, any questions? N3? Okay, yeah, that was my mistake. Any questions on any of these ones? Yeah, what is it called? The radical. So yeah, so here we form a mono subalkene, here we form a disubalkene, but on the left we form a secondary radical, whereas on the right we form a primary radical. So yes. And then the low temperature would be like 0 degrees Celsius. So it would be like 0, and then usually for high temperature it's like 50 or 60 or something like that. Oh, like one of the, the facts questions? Yeah, there shouldn't be. You might see like one of the reactions where you have to like do a synthesis sort of thing where you got the blank arrow. Yeah, but you shouldn't get one that's like, oh, look at this compound, state 2 reasons why, etc. Yeah, that you shouldn't see that. Okay, I'm gonna go on to reaction number 4. So we've got a benzene, we got a nitro, and we've got a chloro group, and we've got NaOH. So this is going to be an NAS reaction. And so for NAS, you want to replace you're going to replace a chloro or bromo group that is ortho or para to the electron withdrawing group. So this chlorine is ortho to the nitro group. And so that just gets replaced by whatever the nucleophile is that's being attached. So NaOH, our nucleophile is going to be OH. So we've got this. And then you'll notice that she said 2 equivalents for this one. And so what this one is going to do is the second equivalent is going to deprotonate the oxygen. So although it would form an alcohol initially, the second equivalent is going to deprotonate that, and so we're going to get a O- here. And then the second step, we have CH3CH2Br. And so if you'll remember, an RO-, so an alkyl with an O-, and then a alkyl halide is going to be the Williamson ether synthesis. So this is just going to attach the alkyl part to the O-. And we're going to get our ether. 1, 2. All right. And then step 3, this one is going to be our Birch reduction. And so this one is going to reduce the benzene to a diene. And just remember that the electron withdrawing groups are going to be the ones that go to the sp3 carbon. So they're going to be the ones that are reduced. And that just has to do with how the electron pushing mechanism works and favors the formation of that. So I like to just draw my structure, however it was in the cyclo ring. Got our NO2 here. And so since NO2 is an electron withdrawing group, that one's going to be on sp3 carbon. And so we're going to put the double bonds on the other carbons. Okay, any questions on that one? I'm going to move on to the next one. So, the second step right here. Yes, so that one's, oh, the second equivalent of the NaOH. Oh yeah, this one's the Williamson ether synth. Yeah. I believe that's in the ethers and epoxides chapter. I think that's 14. So you can find it in there. Okay, reaction 5. We've got an ester, we've got NaOET and ETOH. I love that. So this is going to be Claisen. And so you can recognize Claisen if you see a ester in the beginning structure. If you had just like a ketone or something, it might do like aldol. But since we have since we have an ester, it's going to be Claisen. So you can memorize the names of them. I never really felt like that worked very well for me, so don't feel obligated to. But what this one is going to do is it's going to deprotonate, and it's going to attack itself, since we just have the one structure that she's given us. Okay. So we're just going to deprotonate an alpha hydrogen, and that's going to attack itself. So that's going to attack the carbonyl of the other equivalent. That's going to kick the carbonyl up, And then what happens is the carbonyl actually comes back down and it kicks out the ether part of the ester, because that is a good leaving group compared to like an OH for carboxylic acid. So we're going to redraw this. Okay, so again, we kicked out the ether part of the ester. So we've removed that O, CH2, CH3, and we're just left with the ketone instead. So then another equivalent of the NaOH, NaOET is going to deprotonate the alpha hydrogen that we formed right here. And so anytime for Claisen, if it just has one carbonyl, so in this beginning one, we just have the one carbonyl right here, you're going to want to have it attack itself first before you go on to the next step. It's always going to form this like dicarbonyl with the one carbon in between. So that's going to give us and then this is going to be deprotonated. So now that that's deprotonated, we can go on to step 2. So this is all step 1. And so that's just going to attach the CH2, CH3 onto where that the deprotonated carbon is. We've got CH2, CH3. These ones are always wonky to draw, so I apologize if you need me to like clarify where things are. Please just ask. So now I've got 1, 2, 3. Okay. Now I've got this, and then our last step is going to be the decarboxylation step. And so this is going to be H3O plus and high heat. And so this is just going to entirely remove the remaining ester part, including the carbonyl carbon. So we're basically just going to cut it off of the molecule. So I'm going to number my carbons to make sure everything is right in the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Carbon 4, 1, 2, 3, 4. Okay, so that is going to be our final product. So this one definitely is a lot. Oh wait, I forgot. That's CH2, CH2. This one is kind of a lot, but if you follow the pattern, you should be good. Any questions on either of these two? If it has more than one carbonyl, so if you're given something like this, then you just go ahead and deprotonate it and then immediately react it with like the alkyl halide. Okay. All right, I'm going to go ahead and move on to mechanism. All right. So for this mechanism, it looks like we did a ring formation over here, and it looks like we form an enone. So this looks like, to me, it's going to be an aldol dehydration. So for the first step, as always with NaOET, we are going to deprotonate an alpha hydrogen. So we can have one of our OETs, and since this one's symmetric, it doesn't really matter which one you do. So we're just going to take off a hydrogen and form our carbon ion. Theoretically it could, but if we look over here, we know that we're gonna have to, yeah. If we deprotonated the cyclohexane one, it'd probably just form like a propyl, a cyclopropyl. So it kind of depends on whatever the end product sheet gives you is. That's a good question, though. I forgot to mention that. We've got our carbanion. All right. And so then we're going to have this carbanion attack the other carbonyl. We know that we want to attach this ring together, and then also that carbonyl is going to be a good partial positive electrophile. So that's going to kick up the carbonyl. We're going to get our O-, then we're going to form there. And then also coming off of that carbon, it's going to be, I don't think I drew that right. Yeah. So we've got the okay. Sorry, that was a struggle. Okay. So we've got our O- now, and we've formed our ring. So now we just need to figure out how to get rid of one of those carbonyls. So we have this O-, and so we also have ETOH in our solution. So this O- is going to protonate itself with that, and we're going to get an alcohol. And we get our alcohol. Got our carbonyl. Okay. So from here, this is where aldol and the aldol dehydration gets a little bit different from like a standard E1 or E2. So normally you might think to protonate the OH and then have the water leave and then do like an E2 reaction. But the aldol actually goes through a different mechanism. And so what happens is one of our OETs takes off a hydrogen adjacent to an alpha hydrogen adjacent to the carbonyl. So we're going to remove that hydrogen, and that is going to form a double bond to the carbonyl and kick that carbonyl up to form our enolate. So we've got our OH. All right, so we've got our double bond there and our enolate anion. And so then from here, what the dehydration does is the carbonyl comes back in, that shifts the double bond over and actually just kicks out the alcohol as it is. So again, this is very not like the other stuff that we've looked at. But this, and then we get that. So there we've got our final product. So mine's flipped upside down because I guess I should have done the top one, but either way, it's the same. So any questions on that mechanism? Mm-hmm. I mean, just kind of because it's the aldol, like reagents and stuff. You've got your carbonyl and your deprotonated alpha hydrogen and the NaOET. If you see something like this where you've got your enone formation, just know that it's going to be aldol, and then just remember that aldol is a bit different from the normal E2, and that's just because it forms the enolate. The enolate is kind of what makes it different. Yeah. So if we didn't have heat, we would just stop where it forms the OH, but then the heat kind of lets it keep going and form the enone. There's honestly a lot of options that she could do. So you could do aldol, or just aldol and dehydration. Yeah, she could do the enamine and the imine. Do you think Michael? Yeah, I think I remember that one. So work, and then wasn't there a Wolf Kishner? Or do you think that's exact? Okay, I've seen it. Oh yeah. Oh yeah, you're right. Okay, so you got all these different options. Most of these, like James said, you guys had the acetal protecting group one on your third exam, so you're like 99.999% not gonna get that again, unless she's feeling really nice, which no. The acetal formation, the one where you do the diol and then it does the protecting group. 3. And then, so this one was aldol and the dehydration, Stork, Robinson annulation, which is at the very end of chapter 22, like the last page of chapter 22. So these are a few options that you can look at. Yeah. Okay, any other questions on the mechanism? Okay, we'll go ahead and move on to our synthesis. So for synthesis, there's also a few options, especially like any of the enones, aldol, claisen, especially for this one, Michael is a pretty good candidate. And so you'll see that in this one, we actually do have a Michael reaction. So you see we've got a lot of carbonyls and stuff going around. And so one thing to notice about Michael is that it does an alpha beta, I guess alkylation you could call it, where you attach the carbons together. But sometimes with the Michael, it doesn't initially look like it might work. But remember that Michael reactions, you have your donors and your acceptors. So donors are going to be like what donates the electrons. So like any of our carbanion stuff that we've worked with so far. And then we have acceptors. And so one of the most common ones that she puts is the enone. That's a good Michael acceptor. And she has a list of good Michael acceptors at the end of chapter 22. So I recommend looking at that. But for this one, we're going to cut it here. And we have NaOET. And our first half is going to be this benzene side. We've got our fluorine. We've got our carbonyl. And then this one's going to be our enone. So we've got 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. And then the other half is going to be the one that attacks. So this would be like our acceptor. We've got that enone. And then the donor, and you don't have to label them, I'm just labeling them for you guys. It's going to be the other half. So we've got this carbonyl. We've got this alpha hydrogen in the middle. Got another ketone. Yeah, you'll see that we have the 2 carbonyls here. Okay, so then you can choose either side you want to work back first. I'm going to go ahead and start with the right over here. So kind of similar to the reaction section that we looked at, this is going to be a Claisen condensation. So we have our ester, and then we have, this is going to be like our little backbone that we got. And one way to kind of work with these ones on synthesis is to kind of do that step in the forward direction to just check yourself and make sure that you've got the right compound. So if I quickly do that over here, we've got deprotonated form, got our normal one. So that would attack, pick that up. and then that would come back down and kick out the ester. Then have this. So again, it looks a little bit wonky because I'm always bad at putting them in the right direction. But we do form the same compound that we have right here. So this one's just going to be a Claisen with itself. So that makes it a little bit easier on us. We only have to draw one of these. And then you're just going to do your NaOET, ETOH over the arrow. And then you're going to be good. Okay. And you don't have to do 2 equivalents or anything like that. This will be fine. Just the NaOET, ETOH. If you want, you could put 2, but I don't think you would get points off if you didn't. Okay, so then we have an ester. And so what we can do for this is we can do our ester formation. So like our Williamson ether synthesis. So we've got CH3, CH2, OH. So that's going to be our ether part. And then H plus for Williamson ether synthesis. And so going backwards, we can just do a carboxylic acid. It doesn't have to be anything fancy. All right, and then working back from this, we got a 1, 2, 3 carbon alcohol. And we can just do like Jones reagent or any of the strong oxidizers, and then we are good to go on that side. I probably should have looked at this first, but we've got benzene, aniline, alcohols of 5 carbons or less. So we're good to go on that. Now we just have to work back the other side. All right. So for this one, we have an enone. So what we can do is we can do like an E2 reaction, sort of. So we can work this back. We've got our fluorine, and we can do an E2 reaction with a good leaving group. So I'm going to do a halide. Bromine is a pretty good one. And then for this, since it's just an E2 reaction, you could do any strong base. I'm probably just going to do ETO-. That's a pretty good one. You could use like TB-toxy as a good one to memorize, but sometimes that forms like specific less substituted alkenes, so you'll just have to watch out for that too. And then here, so here we have a bromine right next to a carbonyl. So this is going to be our special Br2 acetic acid reaction. And what that does is it just puts that bromine on that the carbon right next to the carbonyl. All right. So then from here, we can do a Friedel-Crafts. So we've got our acyl chloride, and then we've got AlCl3, and our previous step is just going to be this fluorine. Yeah, I'm going to work this back first just because it's a little bit easier. But if you do synthesize an acyl chloride, you will still have to work that back, so don't forget about it. And so that's all a good reason to do it first too, just to make sure you don't forget about it. But for this one, we can just do our SOCl2, and that would replace the OH on a carboxylic acid. And then from there, we have 1, 2, 3, 4, 5. So if we just work this back to a 5 carbon alcohol using a strong ox, we are good to go on that one. Got that one. Okay. And then for this one is going to be one of your chapter 19, the sodium, or not the sodium azide, one of your nitrogen weird reactions on the benzene. And so this one is going to be your HBF4 and heat. And so that replaces the weird little group that we formed. I don't even remember what to call it, but the nitrogen, what is it? Diazonium salt. Cool, great. Okay, so, and the way we can form that is we start with a aniline, and you'll notice that that is allowed in your starting material. So you start with an aniline, and then you do NaNO2, and HCl to form that diazonium salt, and then you can work it forward. So since we're allowed to start with this aniline, we are good to go. So yeah, lots of new stuff in this one, so yeah. You might be able to do like a reducing reagent, but I think if she wants you to do one of these like diazonium salt ones, she's probably just gonna let you have aniline, because yeah, there's already a lot of stuff that's going on there. Yeah. Yeah. She does say, I think, on the key, she says no extra credit for synthesizing allowed starting materials. So, yeah. The NaNO2 one? I would probably show the intermediate, like the N2Cl minus. What do you think, James? Show the intermediate N2? That's what it shows on the key. So I think, yeah. So you will have to show the N2. You can just do N2 plus Cl minus. You don't have to show the triple bond. But you do have to show the intermediate step, yeah. Oh, like I think I know what you're saying. Oh yeah, like the FeBr3 thing? Um, Perhaps. On my key, she used the HBF4 one. It's CF3. See it on the CF3, they said. Yeah, I'm not quite sure what you're talking about. I'll see if I can find it afterwards. Okay, James will come over. Yeah. Starting from here. hmm So let's see. I guess I would say if you have an ester on one side and a ketone on the other one, that's kind of a hint towards Claisen. Just because Claisen is the one that does that reaction where it attacks and then the ester is kicked off. So maybe like a way you could check it is like if you attach like whatever the other part is. So we have this O and then we have 2 carbons, and then you like kind of compare them. You'll see that we have 1, 2, 1, 2, 3 here. 1, 2, 3, ester 4, 5. 1, 2, 3, ester 4, 5. So you can like check it like that. Yeah. Okay. Any other questions on this mic? Yeah. Or sorry, Synth. Yeah. So One thing to look for is for esters. That's just a hint towards Claisen. And so Claisen, the ester group gets kicked out. And so what I was saying is that if you want to like check, you can like theoretically attach whatever the ester part is to that other carbonyl to see if it matches. So here we looked at this one and we saw we have 1, 2, and then the ester 3, 4, 5. And then here we got 1, 2, and then the ester 3, 4, 5. So those ones would be equivalent, and so then you can just go back to the one equivalent. Okay, I'm gonna go ahead and move on to spec. Spec. Okay, so luckily for spec, there's not too much else that we've learned that we can throw on here. At most, you might see like an amine group or an amide group, but those aren't very common in the test that she makes. So we'll just go ahead and start as always with our unsat number. So we've got 2 times 7 plus 2 minus 12 all over 2. So 2 times 7 is 14 plus 2 is 16 minus 12 over 2, that's 4 over 2. So we've got 2 unsats. So that's pretty low. So we know we don't have any benzenes because we need 4 more for benzene. And if we look at the IR, we don't have anything in this region, so we know there's no alcohols. This is also the NH peak too, so we know we don't have any NH2s, but we don't have a nitrogen anyways. And then over here in the 1600 to 1800 range, we've got a couple of strong peaks, so these are likely going to be some carbonyls. And then going to kind of skipping ahead to the carbon-13 NMR, we have these 2 peaks that are very far to the left. And so this isn't the table that you'll have on your exam, but I just pulled this off the internet. So if we look right here, we have a ketone peak that shows up at about 200 to 220. And then we have a ester, like ester derivative sort of, or sorry, carboxylic acid derivative at like 165 to 185. And so you'll notice down here, this one's at about like 165 to 185. And this one's at about like 200 to 220. So we know that we're going to have a ketone, and we know that we're going to have a ester. Right. And so that would take up all of our unsats. So we know that those are going to be our unsat numbers. We're not going to have any alkenes because we have these 2 peaks telling us these carbonyls. So we know that that's going to be where our unsats go to. And then looking at the proton NMR, I like to start from right to left, but you can do it however you'd like. So we've got a 3H peak triplet. So this is going to be a CH3 with 2 neighbors. We have another CH3. This one's also triplet, so it's also got 2 neighbors. We have a 2H, we have a CH2, and it's got a quadruplet, and so that's going to be 3 neighbors. So this could be one of these 2 CH2 peaks that we're looking at, like maybe this one or maybe that one. We have a 2H that has nothing, so this is going to be a CH2 with nothing on either side. And it's also pretty far downfield. Then we have a CH2 with 3 neighbors that is very far downfield. So it looks like our pieces are kind of lining up. It looks like we've got some stuff that kind of matches here. We do have the CH2 that's kind of in the middle of nowhere. So with these puzzle pieces, I'd probably look at this one over here down at like the 4 to 4.5. And so I know that if it's super far downfield, it's likely going to be attached to something that is electronegative. So maybe like a carbonyl or an oxygen. And since this one is so far down to the left, this one is definitely going to be connected to an oxygen. And you can also use the table that you get to kind of confirm this. So if you see down here at the very bottom, we have our alkyl group connected to an oxygen, and that's at about 3.3 to 4. And so if we look at this one, it's even a little bit further downfield, but we do have a couple peaks that are down here. So it will be attached to something pretty electronegative. Other thing, the next most downfield one is going to be the CH2 one in the middle of nowhere, and we know that it doesn't have any neighbors. So the only thing that this one could be attached to is our carbonyls. So we know that we've got two carbonyls. One of them is going to be an ester. And the reason why I'm not connecting this CH2 to the oxygen part of the ester is because it's downfield, but it's not as downfield as this one. So I know that this one over here on the left is going to be the one that's connected to the oxygen. And so using that, I can say that this one is going to have the CH2, CH3 coming off of it, because that's going to be like this little puzzle piece here. And then for the other side, we've used up our OCH2, CH3, so that's one of these guys. We've used up our CH2 in the middle, so the only thing left we have is this additional CH2, CH3. And so this peak is a little bit downfield, not too much, but it is downfield, so that does make sense with the structure that we have. So let me just redraw real quick. So we had the CH2 that was connected to the two carbonyls. We had the ester part that was attached to the CH2, CH3 because that CH2 was super far downfield. And then the only puzzle piece we have left is this CH3, CH2, and that's going to be connected to this carbonyl. And again, it's kind of reinforced by the CH2 being a little bit downfield. So that is going to be what we throw in the box. Okay, any questions on the spec? Yeah, at the bottom with the carbon-13. So, like I said, your thing will be different, but you will see there should be some characteristic peaks around 165 to 185 for an ester or a carboxylic acid. And then the ketone is even a little bit further past that at about like 200 to 220. Any other questions on the spec? Okay, so I guess we'll call it good for that final. If you have any other questions, let's take a 5-minute break for any questions for this one, and then we'll do some practice with the ACS part. And then you guys can leave, you don't have to stay.